So, the last speaker of our this afternoon is Andrii Liashyk, who will speak about new constructions of Bethe vectors.
Can I speak now? Does someone hear me? Yeah, it works. Yes, it works. Yeah, so hello everyone. I want to say, yes, I'm happy to be here. I appreciate to all organizers for invitation. It's a big honor to me. So I want to talk about some construction of Bethe vector. It was known 15 years, maybe more, but was not realized potential of this construction and how much good physical stuffs can be calculated using this construction. And I want to present this story to you. Maybe someone of you finds something interesting for yourself. So, okay. So we start with usual case, GL2, sorry. We use the most simpler R-matrices. We have usual algebraic Bethe ansatz. We have 2 by 2 Mondev matrices, and it satisfies RTT relation. It's usual stuff. And we works in algebraic Bethe ansatz approach. It means that we suppose existence of some pseudo-vacuum vector with some special properties, that lower part of Mondev matrix annihilate him, A and D act as in diagonal way, and operator B produce new states. It's like creation operator, so it's usual. And when your operator C, A, and D act interval way onto vacuum, you have only one possible way to choose choose constructions. It's just product of BBB onto vacuum with different spectral parameters. So when you have GL2 case, there is not so much freedom to choose. And we start with this, and usually it succeeds. So it was known if you act by transfer matrix, switch trace of Mondev matrix onto Bethe vector, and parameters satisfy Bethe vectors, then our Bethe vectors becomes eigenvector for transfer matrix. So I hope so. It's very known, simple story for everyone. And what if we can change coordinates onto Mondev matrix? So we make something like Gauss decomposition of Mondev matrix. So just formally for GL2 cases means that we make a substitution like shown in this formula. Formally, it means that we decompose Mondev matrix in product of 3 matrices, upper diagonal, and lower diagonal matrices. And then what happens with, and we try to look what happens with commutational relation. So RTT relation can be rewritten in terms of this operator in this way. You have these 8 relations, 6 here, and 2 more here. So we can rewrite RTT algebra in these 8 relations. And this some way to, you think about this Gauss decomposition like just change of coordinates onto Mondev matrices. And just another stories. Yeah, so if you substitute this construction to Bethe vector, usual one, BB, you becomes to this huge formula, which is not so nice. It's worse. It looks worse than previous one. Nevertheless, you still can work with it. But I make the claim that this formula is exactly the previous one when we substitute our Gauss decomposition representation and commute all k to the right to vacuum, annihilate to produce this lambda, and that's it. So this formula not so good to work with it because you can't calculate stuffs. But there is a way to fix this complexity to rewrite in another. So there is some way to simplify this representation to use auxiliary stuffs. So to do it, we Yeah, so there is f. Yeah, so f is part of Gauss decomposition, so if you see this story, this b it's f over multiplied by k. So BBB it's product f's k, fk, fk. Then you use this commutation relation this from the second row. You commute all k to the right. You have a lot f's, so you change one k to two f's, and each term grows number of f's. And finally, you have product of 1f, 2f, sum of n minus n f's. So we have some triangular complicity of f's. Yeah. So its functions, its operator. Yeah. So to fix this complicity, we introduce double Yangian. It's very known from mathematician's construction. Nevertheless, if you try to release it, you can think that you have just two copies of RTT relations that connected with each other. So there are four RTT relations: for plus Mondrian matrices, for minus Mondrian matrices, for plus minus, and minus plus. So it's like RTT, but connected one. And for each Mondrian matrices, you can consider Gauss decomposition, and then you have 8. Yeah, no, it's not the different example. It's the same example. I tried to explain how you can simplify GL2 So how does this construction work on GL2 Because for higher runs, you can explain it on Blackboard. It takes a lot of times. Maybe it's one case when you can understand everything clearly. Maybe also GL11, but not now. Yeah. So you start from RTT with one Mondrian matrices with 4 operators, and now you have 2 Mondrian matrices with 8 operators that called k plus minus 4 and 2e, 2f's. Is that okay for you? Yeah, okay. No, I think that let's consider GL2 case. We choose 2 GL2, one we called T plus, another we call T minus. They have the same R-matrices, and moreover, they connected by some plus minus RTT. So in this sense, it's the same construct. It's the same story. So you can think that T plus it's our start initial Mondrian matrices, and T minus it's some external Mondrian matrices. They somehow connected with this one, but it's a separate one.
But it takes from the same space?
All our constructions works in such way when T minus never act. So for us, it's somehow formal construction, for formal part of story. Yeah, so now we introduce full currents. We define it like difference between F plus and F minus. And let us introduce the most important component of our construction, its projection. Was invented by Horoshkin, nevertheless. So if you have some huge term with F minus, F plus, please try to reorder all F minus to the left or plus to the right using commutation relation like such type. So you see that it's possible, because if you have F minus on the right and F plus on the left, you apply this commutation relation, put F minus to the left, F plus to the right, and it's okay. So, and you repeat it after the end, and you can repeat it also because it's strictly procedure. And at the end, you have some term which normal order in this sense, when all F on the left or F plus on the right. And then projection is some operator, some procedure operator, etc., works in next way. If you have any f minus on the left in your term, then it should be gone to the 0. It should be put it to 0. If your term only with f plus, it's still alive. So it's absolutely formal procedure. Yeah. And my statement that this huge formula with many products of f's can be written in compact way using this P plus procedure, P plus projection. So you can see that you have product of f plus minus f minus times f plus minus f minus, and et cetera, et cetera. Then you can expand the brackets, and then reorder in each term. You should reorder operators. Put all f minus to the left, all f plus to the right, and in the end you have some lot of terms which equivalent to this previous formula, this one. So it's absolutely formal procedure, but it have amazing mathematical properties from quantum algebra. Yeah. So you can write, so you can try to understand this procedure. So it's for a moment just formal procedure, but it can be proven that it's the best and very convenient to use it. Yeah, but yeah.
So, for example, you started from BBB on omega, right?
Yeah.
You created that complication by introducing the set, and now you solved it again by introducing.
Yeah, but it's some invert logic because, of course, it was not invented in GL2 case. It was invented in higher runs. But to prove that higher runs, this procedure equivalent to nested Bethe ansatz procedure or trace Farchenko formula, it's very hard problem, very hard combinatorial problem. It's done, but it's very hard. And there is no possible way to explain it in a few hours. It's really huge works. But I can explain how it's worked for GL2 at least. Yeah, so let me say how it's some points. So this representation, called quantum algebra, was invented by, it's called new representation of Yangian, invented by Ding-Frenkel in '76, maybe something like that. So it's somehow very natural way for mathematicians think about quantum algebras, for RTT relations, but from absolutely opposite side. For centuries, I mean, okay, for last century, mathematicians invent a lot of things about quantum algebra, and usually physicians can't apply it because it's absolutely another language. But this construction allows you to apply mathematical property of quantum algebra to physical stuffs like Bethe vector, etc. And it can be done, and it's done. Yeah. So it was the GL2 case. Okay, so let me explain. Let's say, so for the next, we can consider some RTT relations when our Mondor matrix is n by n matrix. And it can work more or less for wide class of R-matrices, even not differential one, with not difference depending on spectral parameters, but wide class actually. And our R-matrices for first order should satisfy Yang-Baxter equation. It's condition of consistency of our algebra. Then we ask, then standard story that we can produce transfer matrix which is trace of Mondor matrix, and its commute, and its way how RTT relation produces some integrable system. You pick up this transfer matrix, expand in some area, pick up some coefficient, and call it Hamiltonians. And sometimes it's very nice, sometimes no. Yeah. So as I work in algebraic Bethe ansatz, it's crucial point for me to have vacuum vector. And for me, vacuum vector it's a vector with following properties. All lower diagonal elements of Mondor matrix act as 0 on this vacuum, and all diagonal elements act in diagonal way. So this vacuum is eigenvector for all diagonal part, and I can lay by its lower diagonal. Yeah. And then, yeah, at the same time, I don't speak about some representation. It's not field representation. It's not vector representation. It's something like high weight representation for algebra, this one, but without specification. It's finite or infinite or something like that. Yeah, that's my approach. So it's my framework. And so as your all operators except upper trigonal law act in some trivial way onto vacuum, all freedom what you have, it's act by upper trigonal elements onto vacuum and try to construct some beta ansatz beta vector. It's done for wide class algebras. Usually it's called nested beta ansatz. It's some construction, very inconvenient to use it, but there is. But I want to propose another construction which equivalent to this one, but with very, very better properties, it seems to me. Yeah. So the crucial idea, it's Gauss decomposition of modern matrices. It was done firstly by Ding-Frenkel in '93. They use trigonometrical version of this story, but it's not a big deal. So you have RTT. You have such type of R-matrices, Yangian R-matrices. The most common one for GLN case. You can pick or consider this RTT relation. It's just some components of RTT. Yeah, it's OK. Then you consider Gauss decomposition of this story. So you want that your Mondor matrices, it's product of upper diagonal, and lower diagonal matrices. So it's crucial point. Try to understand me that I read it a few times, but it's a really crucial point. If you can do it, if you can decompose it, and you can rewrite RTT relation from this form to some very familiar from mathematicians that's called second differentialization one, then you more or less succeed. Yeah. Then you can use some standard approaches and you can calculate a lot of physical stuff. Yep. So direct answer was done by Ding-Frenkel isomorphism. That your diagonal part, your k, I, j, they compute. So we call it Qunatum part of algebra. Then very natural thing that f, it's part of which call positive barrel. E, it's another part that we call negative barrel, but okay. And they have very the same computational relation as for GL2. So this part, like GL2, so elements near to the diagonal, they act as GL2. And if you're familiar a little bit with representation theory, it's a very natural way to act. And the difference, when we try to compute this E with neighborhood, when GL2 case, you have only one E, one F. So there is no problem. So there is no question to compute E with another E. In our case, answer that E, it's simply one, so it's the closest to the diagonal E. They compute if distance more than 2, so E compute with E plus E I, compute with E I plus 2, and etc. But it's not compute for the closest one. And this is the answer. And we need this formula if you try to, because we need to reorder operators, F minus to the left, F plus to the right, and we need formula of such type. It's not whole algebra. There is much more complicated computation relation, but the most important is this one. In some sense, they define algebra in unique way. The other can be constructed as consistency of this algebra up to some serial relations, but it's some story, don't worry. Yeah, so surprisingly, but formula have absolutely the same form as for GL2 case. But in our case, we have not only one F, but we have n minus 1 F. And if you're familiar with stuff like nested beta ansatz, you know that for GLN case, you have n minus 1 type of beta roots. You say we want R1 type of first one, and up to the last one, and we want Rn minus 1 roots of the last type, and then you put f's of each type with E, with some own spectral parameter, put in put in some product, and then use the same procedure, just projection, f minus to the left, f plus to the right, and then these constructions produce you nested Bethe ansatz or trace Farchenko approach, the same off-shell Bethe vectors. So this formula is equivalent to nested Bethe ansatz, to Tarasov-Farchenko constructions. Nevertheless, this simple idea, not idea is complicated, simple representation for answer, but it's produce you the same story. It takes some experience, it requires some experience to work with it, but to show you answer, not so much problem. Yeah, so using this, so there is some question can be here. Can we change order of f's? And more or less, up to some normalization, it's not change anything. So you can put in any order, and it's not affect on your algebra, on your Bethe vector. So only up to some normalization. So there is no much freedom. You put f's in any order, and it works. And me, with my collaborators, to show in some papers how this construction can be used for calculate actions of modern matrix entries onto Bethe vectors, scalar products, some norms, sometimes even determinant forms for on-shell off-shell Bethe vectors, sometimes no, sometimes determinant representation for form factors of local operators, sometimes no. But if you have such type of formula, you always can do something like off-shell scalar products in terms of partition functions and norms, Tij action onto Bethe vectors, etc. So it's much more than can you do from Tarasov-Farchenko construction or usual nested Bethe ansatz construction. Yeah. So, yeah, and it was known 15 years ago it was opened by Khoroshkin, Pakulyak, and Rikis. It was very old science. A story about physical stuffs, it was done by me with my collaborators, but nevertheless. And last few years, I spent my time to try to generalize this construction to other series. So we consider this Zamolodchikov R-matrices. This is the most common one, so it's for SP, for SO. And we prove that you can use, so before I say the answer, I want to admit a very, very important part of story. So you see, these R-matrices have two poles, not one. The second poles have a residue with rank 1. So this Q operator, very tricky one. The square of this operator is n, so it's projector in some sense. So square of Q is nq, sometimes minus nq, but it's details. So square of this operator more or less proportional to themselves. And rank of this operator is 1, and it's transposition of P. And it's, for symplectic case, it's transposition with some signs. Yeah, and existence of this Q for SP, for SO, for orthosymplectic algebra, a lot of examples, always give you some center of algebra. You can think about the center as quantum orthogonal condition. You have orthogonal algebra, it's okay to have something like orthogonality, at least in quantum sense. So it's provide you something like that. And if you try to inspect this algebra for current level, it's very, very nice connections between simple currents. So if you have n by n Mondrian matrices, you have n minus 1 simple currents, and this orthogonality is not up to main diagonal, but the second diagonal. So it's give you some sort of like connection between the first and the last current. So it's, in quantum sense, say you that your Mondrian matrices is symmetric up to second diagonal. It's something like this one. It's hard to think about this condition in this way, but if you try to inspect in current level, you see something like that. F equal F prime, which oppositive current from another side, up to some shifting. And this shifting is its quantum part of story. It's calculation. It can be proved, but it's calculation. Yeah, so in this sense, you start from n-1 independent simple current, but quantum orthogonality condition, this one, restrict the number of independent full currents in 2 times. So more or less, it's n over 2 independent full currents. And in this story, at the end, one can prove, we do it, we did it, answer that Bethe vector is product of independent simple currents with corresponding spectrum parameter, and the same way as previously. So now we have received, in this case, you make Gauss decomposition, pick up simple currents, make double Yangian, construct full currents, write a product of them, reorder such all F minus gone to the left, all F plus to the right. Then you apply projection, and then you apply this huge formula to the vacuum, and it's produce you Bethe vector. And its formula looks like previous one. And it's very, very amazing part of story. So more or less, answer is the same for whole algebras, A, B, C, D type. And there is paper of Reshetichin and for Martins, I don't remember with him, maybe with Ramos, but I'm not sure. And they have something like nested procedure for other series. And I try to compare this construction for small ranks as they coincide. But I don't try to even compare it for high rank because it's very, very hard to work nested Bethe ansatz for other series. Yes, I don't like it. Yeah, but my formula, amazing. Work the same as for GLN case. It's give you scalar products, norms, action of Tij onto vector, etc., etc. So if you can calculate something for GLN using my approach, you can also calculate it for Bn, for Cn, Dn. Actually, it's applied for much more wide class of models with natural symmetry, like algebra symmetry or something like that. But let we restrict ourselves for the moment. Yeah. So for this conference, I tried to, it was my whole idea to apply this approach for Hubbard model. Yeah, it was actually a challenge problem. And we should to start from something. So we start with Bézard R-matrices. It's not usual form, but you will see. So one can separate Bézard model in three terms of different type. First, so it's some notation, usual one. If you're familiar with Bézard paper, with Bézard R-matrices, it's the same one. But I prefer another choice of grading because if original way they haven't good Gauss decomposition only in this way, only with this. You should have symmetry between term position by second diagonal. So yeah, in Bézard was 1 and 2 was this grading 0, and 3 and 2 was and 4 was this grading 1. So it's a little bit another grading. In the rest story, it's more or less the same. Unity is slash operator. So you see that it's like diagonal, but with some functions. Here you have something terrible actually. But in some sense, if you consider residue u equal v and put v to the infinity, it's unity. So it's proto-unity, you can think about it. P looks like the same. So up to some numerator which never, yeah.
What is the meaning of that previous operator? This one?
Yeah, so I say, if you start with,
This is the first one.
yeah, it's first term of my representation of Bethe R-matrices. Yeah. So I just tried to think about Bethe R-matrices as one more orthogonal like R-matrices, but with some stuffs. Yeah. And its P part, it has residue at point u equal 1, and residue is exactly superpermutation. So it's, yeah. And Q, it's such type of operator. It has a residue in special procedure. So you should put, they called it procedure like conjecture, yeah, no, conjugation. You put x plus minus of u and x plus of u to 1 over, and then you have pole at this point. Yeah. So it's such type of operator. So you can think about this in this way. So 1, if you put u equal v, put v to infinity, you become unity. P, it's operator which have residue with superpermutation and something more. And Q, it's operator which have pole equal to some Q, similar to previous one, with gradient, with superstory, but only after this conjugation of one of parameter. So it's such type operator. Yeah, so it's such type. And you have this very standard story for super case. If you have something like gel n, your q square, it's not proportional to q, but equal to 0. It's the same for OSP nn and for some other type of algebra, but it's okay. It's in some sense, if you can say about superalgebra rank, it has rank 0. And it's skew transposition with some signs of P. I will explain it a little bit later, but nevertheless. Yeah, so you can think about this Shastri, no, Bethe representation of R-matrices in this schematical way, that it's 1 plus P over U minus V plus Q1 with some, yeah. So I tried to say that this R-matrices very close to orthogonal R-matrices. Yeah. So if you have this representation, first your intention is try to understand what is the center of the algebra. And I don't know why. I didn't find it by the paper. They have another center, which some function of this one, but there is one more center of such type. Maybe I miss, but I did not find this center in Bethe paper. Nevertheless, there is paper, there is center, which suppose that there is some constraints on your coordinates onto Mundane matrices, like in orthogonal situation. Yeah, so transposition has this form. It's standard supertransposition for any GLN, but this special part of this gradings, which only about Hubbard, there is no such sign for orthosymplectic algebras. Yeah, so it's some special part, but nevertheless. Yeah, so as I say, the center give you some constraints onto currents, simple currents. So current E34 connected with current E12. Yeah. And there is some connection between Cartan part of, yeah. So more or less, it's with some special points, but it's usual story for orthogonal algebras. Yeah. Then I try to finish Gauss decomposition of this algebra. Yeah, and I succeed. Yeah, you can surprise, but it's done. And if you see for E23, K2, K3, you have absolutely SU2 algebra, absolutely one-to-one, as was shown on the first part of my talk. So you have algebra, and in a part, it's absolutely SU2 with any points, absolutely, yeah. And part with E12 and K1, K2, it looks like fermionic, but with some special stories. It's very fermionic, but not exactly. Yeah, sorry. Yeah, in this sense, it looks like actually, when I finish with it, it seems to me this algebra very, very similar to GL21, but with some special story about E, with this fermionic part. Yeah, so it's okay when E part and F, they dual, so they have the same computational relation up to some details. Then if you try commute E with F, so F with E commute as in GL2 case, they anti-commute as for GL11 case, but functions a little bit not usual, but very close. And then if you try to compute F with E, so it's fermionic, so the UK, it's exactly the same as for GL11. It's the same story. It's exactly the same story for GL22. But the problems begins when you try to compute E1 with E2, E12 with E23. They have so the main part, this one, we called it's the crucial part. These parts have influence on the Bethe equation actually. So it's the most important part. We call it full current. It's full current, and we usually call it local terms because if you see precisely, all these terms have the same spectral parameter. In this point, you have different one, but the same. In some sense, it's important part, crucial part, and the rest, it's some remaining, which usually not important. But in this case, somehow it's turned out that this algebra looks like GL21 when your fermion part live onto two-sheet covering of complex plane. It seems to me it was known any type of such algebra. No one. I asked some special guys, they know, and they say it's something strange, something new. So if you want, truly symmetric of this Bézier R-matrices, it's GL21, or you can call it SU22 central maximum extended if you want. But this is the main point. It looks like GL21 where fermionics live on two-sheet covering of complex plane. Yeah, so it's important part of story. If you mathematics, you like it, you can try to invest in this algebra to try to calculate stuffs, but with physics, usually. And I tried to apply this construction for Bethe vector, and actually I succeed. So I prove that Bethe vector, in this case, also looks the same as previous one. You put full current for F plus, F minus. Put all F minus to left part using this formula. So these coefficients arise, it will arise in coefficients of terms. So it's not so simple, but after all calculation, you have simple rational part and simple, not simple, but this part. But after the end, you have some formula. For in this projection.
Why there are only two types of the
Because the third is connected to this first one. as I say, you pick up only independent currents. And third current is connected to the first one. It's the same story for orthogonal algebra. You have an independent current. You drop all dependent current, and the rest have their own spectral parameters, type of parameters. For GLN, for GLN, you have n-1 type of currents, n-n beta roots type of them. For SO2n, you have only n independent current, n independent beta equations. And in this sense, as this algebra is algebra of rank 2, not 3, 2. Because you have center which restricts one parameter. After all, your algebra is algebra of rank 2 with 2 type of currents. You have only 2 type of beta roots.
So U is not used X, right?
Sorry?
U is not used X.
It's good question, and in some sense, it's of course depend on sheet of choose of sheet.
Yeah, so some of the sets are evaluated on another sheet.
Yeah, it can be. Yeah,
The answer is hidden.
yeah. It's in some sense it's hidden, but so then you can try to calculate action of Mondrian matrices. Trace of Mondrian matrices that called transfer matrices onto this beta vector, and then you become to the formula for eigenvalue of transfer matrix. It's up to some very, very non-trivial factor. It's very, very nice formula for eigenvalue of Mondrian matrix, of transfer matrix. As usual story, you can, from your point of view, you can consider residue of this eigenvalue, and you obtain something like beta equations. I obtain it directly from action of Tij, nevertheless. But finally, I become to this nice, very nice GL21 beta equations. And it's correct answer because it was known from Anches by Shastri. It was very, very known before. But the most nice part of story that in some sense, it should be something like special modification of GL21. Because beta equations, etc., algebra looks like GL21, the rest stuff looks like GL21. So it seems to me that I'm finished. Yeah. So I want to say that if you want idea to understand from my whole talk, that if your beta vector somehow connected this algebraic structure, like Yangian, quantum affine algebra, because this structure work for a lot class, I mean for very, very wide class of models, supersymmetric, not always differential type. I have another examples for trigonometrical, for rational, but always you make Gauss decomposition, but you need algebraic Bethe ansatz approach. Lower diagonal act is 0, diagonal act in diagonal way, upper diagonal is some creation operator. Then you make Gauss decomposition, pick up independent simple currents, build full currents, make projection construction, apply to some vacuum, and then it will be beta vector, even in Hubbard case model. So Hubbard model case, yeah. Left in? Sorry, yeah. So, I'm finished.
Thank you, Liashyk.
It's not very clear. You said your gradient is different from the R-matrix of Bethe. But for example, in SL21 case, we know that when we change gradient, we get different Bethe equation, yes? So it's not very clear.
No. So in this sense, Bethe have something like GL21, but I have GL12.
Ah, okay.
Yeah, but it's a good point. So if you consider vector representation, so I mean fundamental model, there is no big difference. If you consider the whole representation model with non-trivial lambdas, all of them, maybe there is difference, but it's very special question.
I just about right.
Yeah, so I need this change of, so it's not important for Bézier because it's just relabeling of strings and rows and columns. I change the second and fourth columns and rows. So for Bézier, there is no problem. But it's a problem for me because I need that my Mondrian matrices should be skew transpose up to second diagonal. So I need this one, and it's not important for Bézier.
Okay, and the one more question. You said like your method is applied for Y class of model, but somehow in your formula I saw somehow k minus 1 appears. So Cartan are inverted somehow. So does it mean that it will be not applicable if Cartan are degenerate, if it's can?
Yeah. So if Cartan is degenerate, we have a problem. Because you can calculate even Gauss decomposition actually, because it's something like divide to 0. Yeah. So maybe there is another way to think about of this special type of models, but I don't know at the moment. Yeah. Yeah.
So your currents K for Hubbard. So I don't know if you wrote it down, but they also commute for the case of Hubbard?
Sorry?
Ki, they commute for Hubbard.
Yeah,
Yes.
all Ki commute with each other.
Okay, can you diagonalize them?
Sorry?
Can you diagonalize them for Hubbard?
Diagonalize in which sense? In terms of what? I need some representation for this.
Yeah, okay, so for
Yeah.
defining representation. Defining representation, for example.
I didn't try, but I believe, of course, I can.
Okay.
Yeah, because so all my story that you shouldn't care about finite representation if you so it works only for highest type of representation with highest weight type. Yeah, so it's algebraic Bethe ansatz approach. In this case, you shouldn't care about the lowest vector because it's something like model in mathematical sense. You just free action of upper triangle and then you try to understand to find some correct Bethe vector for each shell. And in this sense, I know the answer. You can pick up some special twist. And so I should think about this idea, but I believe that you can do it choosing some twist.
Yes, so the reason I ask is because for Hubbard, this twist does not exist.
Yeah, because in Hubbard there is a restriction. This twist should be
determinant 1 is
yeah.
this, yes.
Yeah, so there is some restrictions for this one. Yeah, so you know better than me. Yeah.
So, okay, well, so you haven't yet tried to diagonalize K. Well, in that case,
I haven't tried.
Okay, so we'll talk later then. Okay.
Yeah, we can talk about it. Yeah.
So answer to your question. So Bézier-Studacher Bethe equations only work in beauty grading. So Bethe equations for this model only work in beauty grading. Trying to do any other grading of the Ding diagram will produce horrible equations. So this only unique choice of gradient, which actually was chosen today as well for R-matrix. Choice of gradient for R-matrix, I mean, you can still get a different gradient for Bethe equation if you just do it cleverly. But this equation is actually, this is GL2/1 rational spin chains. So
Yeah, GL2-1, exactly one.
no, it's not just to 1, but it's a rational spin chain. Where is Zhukovsky?
Sorry?
Where is Zhukovsky? I'm confused.
There is no Zhukovsky.
Sorry?
No, so this paper, very old one, maybe Shastri, maybe no, they prove that Bethe ansatz, in this case, it looks like this one. So it's not new, it's very. Yeah, it was done by coordinate Bethe ansatz. They prove that, yeah, so it's a very old story that we have very, very terrible R-matrices with non-trivial functions, but at the end, Bethe equations have different form. I can show you if you want.
Guys, do I miss something? Where's Zhukovsky?
For Bethe equations, there is no Zhukovsky.
I mean, that is not what we call Hubbard in
Sorry?
this room. I mean, these equations we do not call Hubbard Bethe equation in this room, but I
Oh, no,
agree
I
that
believe
it's
this
historically
equation is
correct.
exactly equation of Hubbard model. I mean, spin chain called Hubbard model. I mean, that Hubbard model, which true Hubbard model.
Oh, okay, like the honest Hubbard model, okay. So the actual question I have, what is your formula for twisted affine case?
Sorry?
For twisted affine case,
Yeah,
your magic formula for B,
exactly the same as for orthogonal case.
but there should some change, right?
You have another R-matrices, so your Gauss decomposition produce you a little bit different commutation relation on E and Fs. But from point of view of formula, you pick up only simple currents, construct full currents, put under projection, and this works. It's work for other series, for twisted, for trigonometrical. It's always one.
So just okay. So you have the same formula. F's are different, but also Bethe equations are different, right?
There are a lot of difference because commutation relation between F's different for each algebra. I mean, commutation relation between of such type between E and E, it's different. So I mean, even this function can be changed, and it's part of Bethe equations. So exactly this function, it's more or less this part of Bethe equations.
Okay, so this magic formula is the same looking, but it have but formula is the same looking, right? This is
For Bethe vector,
yes.
in terms of projection, yes, that's amazing part of story. A miracle, actually.
So does this formulation help to compute the scalar products?
So I finished it in last week, so I don't know, but I believe I can.
But for GLN, for example,
It does for GLN, for other series. I believe it can be done, but I don't want to promise that I can do. But I believe it can be done, and I can produce you something like off-shell Bethe vector scalar product in terms of partition function, like Kershtin formula, if you know. And its formula, more or less, always can give you norms of Bethe vector, at least. Sometimes it can give you overlaps in determined form for on-shell off-shell Bethe vectors, but I'm not sure. But I still don't know, is it GLN 2.1 or it's something another one, because it's hard to understand, but it looks like very close to GLN 2.1.
Well, it seems that there are no more questions, no? So let's thank again Andrii.